In this lesson, we're going to look at log functions. So the first thing we're going to do is we're going to understand where they come from. So an exponential function is where we're going to start with looking at the graphs of those. So let's just do a rough sketch of these. So this first function here, f of x equals 10 to the x. It's going to have an asymptote of the x-axis, or y equals 0. It's going to cross at 0, 1 for the y-intercept. And it's going to grow pretty quick because the base is 10. And then over here, I'm going to graph my g of x, which is our base e function. So again, the asymptote is going to be 0, the y-intercept is going to be 1, but this is going to grow a little bit slower. It's going to be a little bit wider before it starts to go up because the base is like 2.7, so it's not going to grow as quickly as 10 to the x. So this is our g of x, and again, if you want to be more specific about it, you would just pick some points to plot. I'm just trying to get a rough sketch done. And now if you look, the next part says to sketch the inverses of these. So the inverses are actually going to be how we're going to get our log functions. So if you remember, inverses on a graph is when you reflect over the line y equals x. So I'm going to go ahead and sketch that line in both of these graphs. So it's the line that goes through all of the same points. So like 0, 0, 1, 1, 2, 2, negative 1, negative 1. So this is the line y equals x. And in order to get the inverse, we do a reflection over the line y equals x. So that's how we're going to get the inverse. So what I'm going to do is I'm going to take this and I'm going to reflect it. So basically this part is going to end up down here. And then it's going to keep on growing. So this function that we just got, so I'm going to actually write it as the inverse function of f, is equal to log of x. So this new function that we're learning about is called the log function, and it comes from the fact that it's the inverse of 10 to the x. If I look at this next one, same idea, reflect the line. So it should look like it's a reflection. This function, the inverse of g of x, is called ln of x. If you remember algebraically, to find inverses, what we do is we switch the x's and y's and then we solve for y. But if you think of this algebraically, so if I go back to this function here, if I set, so let me just show you, if I set this equal to y, because f of x is like saying y, and then I switch x's and y's, and if I need to solve for y, there's no way that you can do that. There's no y root. But really, when we think about logs, logs are the exponents. So it's asking us, what do I have to raise, what exponent do I raise 10 to get x? And that's called the log. So this is really saying y is equal to taking the log of x. And when I say log, it's really base 10. There would be a little 10 down here, but typically when you see a log with base 10, we just don't write the 10 as a little subscript. So this is like algebraically the inverse, which we'll look at more of that next time, but that's kind of the idea for that. So this is where these log functions come from. These are basically our common logs because here I have a base 10 and we get the normal log that you're used to seeing. And whenever you have a base e, we call it the natural log, the ln. And again, we'll talk more about this later, but that's kind of just to give you like the idea of where they come from. More specifically, what we're concerned about for this lesson is looking at how we went from exponential form to log form. So right here is kind of, you can go either way. And this is really where you want to think of logs equaling exponents. So logs are really the exponents. So what I mean by that is if I have something like this, log base 3 of 9 equaling 2, what this is saying is what exponent do I raise 3 to? So what exponent do I raise 3 to get 9? So the exponent that you raise 2 or 3 to get 9 is going to be 2. So that's where it comes from. So log base 3, if 3 is the base, what do I have to raise it to get 9? Well, I have to raise it to the second power, which is why the log is equal to 2, because the log is equal to the exponent needed to raise this base to equal the number that you're taking the log of. So that's all it really means. So basically, when you're looking at this form, you can go from exponential form to log form or vice versa. So x equals b to the y. The base is the b, and it's the same over here, the base of the log. So if you notice, see how the exponent is really what the log equals. So what power do I have to raise this b to get x? So b to what power gives me x? An easy way to remember like how to go from one form to the other is I remember it as drop the log, swing the base. So switch back and forth. So let me give you that example. So if I start with log base b of x equaling y, basically what I remember is I drop the log, so I clear that out, and I swing the base, and it bumps this up. So it becomes x equals the base, and it bumps the y up to an exponent. So these two things are equivalent. So in here, they're also equivalent. It's the two forms are equivalent to each other, that's just a different form. So let's look at some examples for switching back and forth. So here we have so here's basically our formula for the top row, but then when you get to the second row here, we're given this in exponential form and we want to switch it over to log form. So I'm going to have log, the base is going to be the same as the base as the exponent. So we have 3. What I'm taking the log of, and then the log always equals the exponent. So for this next one, my base is p. I'm taking the log of what I got out, and it equals, the log always equals the exponent, because that's really what log means. Tell me the exponent needed to raise this base to get whatever I'm taking the log of. So this next one, the base is b, taking the log of a so that you can see what the exponent is. And to check these, you can think of it as drop the log, swing the base. So if I drop the log and swing the base to take the 3 as the base, it pushes the n up. I end up getting what I have over in the exponential form. So I think it's harder to go from exponential form to log form because I just use the saying to go from log form back to exponential. But really, if you just remember, the base is always going to stay the same. So 3 is the base. I'm taking the log of 81. I get out the exponent. So then going this other direction, it's a little bit quicker. So drop the log, swing the base. So it's 3 to the q equals x. Drop the log, swing the base. M to the d equals r. Drop the log, swing the base. 9 to the second equals 81, which makes sense. So that's really all it is. It's just using that formula. So this is like the formula up here. So the next thing here is going to be figuring out what x is. So basically understanding it in two ways. I can use the whole drop the log, swing the base thing, or I could just ask myself 3 to what power gives me 27. That's really what it's saying. So what this means is 3 raised to what number gives us 27. That's what it's saying. So there's two ways you can do it. You can just do it by trial and error, or think of it as turn this into exponential form. So drop the log, swing the base. So 3 to what power gives me 27. So the next thing you can think of is if I want to take 27 and figure out what power if I want to take 27 and figure out what do I have to raise 3 to get to that, I can convert 27 as a base 3. So basically what I mean by that is 3 raised to what power gives me 27? Well, 3 to the 3. So since the bases are the same here, the exponents have to be the same. So in order for this to actually be an equation, the bases have to be the same and the exponents. So 3, you could just have looked at it right here and said, oh, x equals 3 because 3 raised to the 3 is 27, or you can convert the 27 into a base 3 and then just see what the exponent is, and that's going to be your answer. So let's try the same thing over here. So it's log base 2 of 64 equals x. So drop the log, swing the base. So 2 to the x equals 64. So again, I'm going to do the same thing where I'm going to figure out what do I have to raise 2 to get 64. So 2 times itself 6 times will get me 64. So now since I have the same bases, the exponents have to be the same in order for that to truly be equal. Or, like I said, you could skip this step and you could just say, oh, x has to equal 6 in order to get 64. So looking at this next page here, we have same idea, drop the log, swing the base. So 25 to the x equals 5. So what do I have to raise 25 to get 5? So this is the one that's a little bit different. So your best bet for this is to take 25 and turn it into some type of expression with a base 5. So basically, think about how I can write 5 so that it equals 25. The answer to that is going to be 5 squared. So I just replace 25 with 5 squared. And then if you remember our exponent rules, whenever you raise something to an exponent raised to an exponent, you multiply them. So 2 times x equals 5. Think about this as there's an exponent of 1 here. So now since I have the same bases, I can drop the bases because in order for this to be equal, the exponents have to be equal. And now I see 2x equals 1, so I just solve for x. So I get x equals 1/2, which you might have been thinking at first was kind of weird to think, well, what do I raise 25 to get 5? Because it's the opposite of what we just did in the last one. I'm going from big to small. So basically, I'm taking the square root of 25 to get 5, which means I'm raising it to the 1/2 power. So this one probably wasn't as obvious to see, which is why you can go through this process that we did in the previous examples. So looking at this example here, we drop the log, swing the base, so we have 81 raised to the x equals 3. So again, it's hard to think about how can I go from 81 down to 3? What power do I raise it to? I know it's going to have to be raised to a fraction because it's getting smaller, but it's not as obvious. So again, take 81 and write it as something with base 3. So 3 to the 4th is going to give me 81. 3 times itself 4 times gives me 81. And then by doing that, now we can use our exponent properties. 4 raised to the x is the same thing as saying 4 times x as an exponent. And remember, you can say that 3 is just 3 to the 1st. Since the bases are the same and since this whole thing is equal, my 2 exponents have to be equal. And then you just solve for x. We get x equals 1/4. So the exponent here, remember that's what log means. Tell me the exponent that I need to take 81 and get 3. And you would have to raise it to the 1/4 power, or basically the 4th root of it. And then this last one here, if we drop the log and swing the base, 6 raised to some power gives me negative 36. So basically if I do this, 6x, I take and I can rewrite this as 6 squared. But then what's going to happen is you don't have the same base. So really, I have 6 to the x equals negative 6 squared. I don't have the same base here, so there's no way for me to solve this. This is not solvable because there's no x that you can get so that you'll ever get a negative 6 squared. So basically, these are not the same bases because one's positive, one's negative. So that tells me that there's no solution to this. So basically, more so what we're looking at for this is there's no way that I can take a number, raise it to a power, and get out a negative number when the number I started with is positive. So since that's the case, you could have said that right off the beginning, right from the beginning. But if you get down to here and you're like, well, wait, these bases aren't the same, so I can't just drop them and say x equals 2 because it's not true. So there's no solution to this, which really tells us that we can't take logs of negatives. If you see here, log base 6 of a negative isn't going to give us a solution. So that's going to be the case, and we'll talk about that more in the future, but for right now, just so you could kind of see it.